He's just like, no, just say it. Okay, so now I'm not going to push the stupid button. Okay, so we're going to start what we call hypothesis testing, which is kind of a weird idea, but it's used more than, I don't know, it's actually used in some sense. And actually, like when I saw Miss Saylor's master's paper and all her thesis stuff, she did have to use some of these. We're going to use a lot of symbols, which makes it a little bit weirder as well. But there are, I don't know why that did it like that. But really what we're doing if we're actually doing statistical projects, we're doing it in words. Okay, so we have a statistical hypothesis is a conjecture about some sort of population parameter. The conjecture may or may not be true. That's like anything, right? So what we have two different hypotheses that we're testing. We're going to have the null hypothesis, which is symbolized by H0. Sometimes, like if you're in science, it's H naught or anything with that zero under there. So sometimes when you see that zero underneath something, it's like an H naught or an H null is kind of not how you say it, but it's a statistical hypothesis that states there's no difference between a parameter and the value that they gave you, basically, and there's no difference between the two parameters. I'll show you what that looks like. That's really wordy for something that is not as gross, so sometimes the words are worse. The alternative hypothesis is what our next slide is all about, and we're going to have an H1 for that. Okay, so the alternative hypothesis, we'll just say H1 is a statistical hypothesis that states the existence of a difference, okay, of a parameter in a specific value, or states that there is a difference, which that just sounds terrible. Again, it's not all that bad. Okay, so if I have, I don't know why this came in through not the same orders. Okay, so a medical researcher is interested in finding out whether a new medication will have an undesirable side effects. The researcher is particularly concerned with the pulse rate of the patients who take medication. Will the pulse rate increase, decrease, or remain unchanged after the patient takes medication? The researcher knows that the mean pulse rate for the population under study is 82 beats per minute. So you'll have some wordy question about like this. So, whoops, I'm pushing the wrong button. So what we're going to say is we have two different hypotheses. We always have two different ones. We always have our null hypothesis and our alternative hypothesis. Pay attention to just like where your punctuation is. So it's H naught, colon, and then we're going to usually have mu equals something, and mu either does not equal something. We have a bunch of different symbols that we can put here. The mu equals 82. The null hypothesis will always, always, always be equals. Okay, that's the one that we're going to see. Hey, is this true or not? We don't know. But this is called a two-tail hypothesis because it's not equal to. Not equal to means two-tailed hypothesis. Increase, decrease, or remain unchanged is not equal to, because we could do a greater than, or we could do a less than, or we could do a greater than or equal to, or less than or equal to. We don't really have less than or equal to's. But there's just so many different symbols that we could use basically for this little sentence in here that we just say, oh, hey, no, that's not equal to. Okay, that's what. Another one. A chemist invents an additive to increase the life of an automobile battery. The mean lifetime of an automobile battery without the additive is 36 months. In this book, the null hypothesis is always stated using the equal signs. I haven't actually seen very many of those where it's not the case. The hypothesis for this situation, so you do H naught equals, let me change this slide to 2. Oh, I already did change that slide. We do H naught equals 36, or mu equals 36, but increase the life. That's what we're looking for. We're looking to increase the life. So we want to see if whatever we're doing is going to be greater than the old stuff that we were told. Okay, so what that looks like, so we have the mu of 36 for our null hypothesis. Okay, the next one, increase, we want it to be greater than. Okay, and there's a whole list of words that I'll show you guys in the book too that is very nice for which symbol to use, because sometimes that's the worst part. Okay, those are how you write your hypotheses. So some of your questions will just simply ask, For each conjecture, state the null hypothesis and the alternative hypothesis. So these would be your answers. We're not doing anything with it today. The next few days we will be doing something with it and testing them. A right-tailed test. So greater than is a right-tailed test. Okay, and the next one is going to be basically the next one that we have to look at. A contractor wishes to lower heating bills by using a special type of insulation. So the key word in there is he wants to lower something. If the average of the monthly heating bills is 78, where her hypothesis about heating costs and the insulations are null hypothesis, mu equals 78. Less than, because I want it to go lower. So my alternative hypothesis is mu equals 78. Or less than 78, sorry about that. What was that? I didn't hear you. Yep. Okay, so less than is left tail. Greater than is right tail. Not equal to is a two-tailed. And I'll kind of show you on some pictures in a little bit how that kind of makes a little bit more sense. When a researcher conducts a study, he or she is generally looking for evidence to support a claim. Therefore, the claim should be stated as the alternative hypothesis or research hypothesis. Okay, so we're usually trying to change a little bit of something. Okay, a claim, though, can be stated as either the null hypothesis or the alternative hypothesis. However, the statistical evidence can only support the claim if it is the alternative hypothesis. So this is a very important piece. Statistical evidence can be used to reject the claim if the claim is the null hypothesis. So we can accept the alternative and we can reject the null. And then there's a whole list of when you basically make the wrong choice. Okay? And those are kind of weird little things. One more little thing in there. The facts are important when you're stating the conclusion of a statistical study. So again, we're not really doing that today. We're just really getting those basic pieces, but this is just where it's going to be used in the future. And I forgot a couple slides at the beginning that was about
tomorrow what we're going to be doing, is that going to be hard?
It's going to be worse, yes. I can go over it with you.
I was going to say, because this doesn't seem bad.
No,
but
this is not bad.
Okay. But when you said it's going to be worse, like, is it going to be hard worse? Or just like...
Very different.
Okay.
Very different.
Yeah, we should probably go over it, because I feel like I'm not understand the video.
Yeah. So what we're going to be doing in the next few days is hypothesis testing. The researcher selects a correct statistical test. So in the next few days, we'll go over like a z-test for the mean, a t-test for the mean, and then a z-test for the proportion. Okay, and those are basically the same types of things we've been doing for each little section. Like the last few chapters, we've had a z-test, a t-test, and then we've had a totally different test for proportions. And then we'll choose as an appropriate level of significance. Remember, that's our like 90, 95, 99% confidence. So that's kind of those sort of things still. And then formulate the plan for conducting your study. Okay, a statistical test uses the data obtained from a sample to make a decision about whether the null hypothesis should be rejected. Okay, so with that guy, am I on the right one yet? That is weird. Am I on? Okay, I'm on this one. Okay. The numerical value obtained from a statistical test is called the test value. In the hypothesis testing situation, there are 4 possible outcomes. Whoops, I was on the wrong one. Let me go back. Okay, so a couple of these choices could be that we're making the right choice. 2 of the choices are we're making the wrong choice. Okay, so we're gonna make like little grids eventually if I can find my little thingy. Okay, in reality, the null hypothesis may or may not be true, and a decision is made to reject it or to not reject it based on the data that we see. And I will show you kind of what actual data it is that we're looking at. And obtained from a sample. Where'd my clicker go? So there's different types of error. Okay. So a type 1 error occurs, let me get to my chart because it's weird to look at it without looking at my chart. Okay, so a type 1 error occurs if one rejects the null hypothesis when it's true. If the first thing you said was true but you reject it, that's an error. That's something wrong. So that's a type 1 error. So just have really clear notes on what a type 1 and then the next one is a type 2 error. And where did my mousey go again? Okay, type 2 error occurs if you don't reject the null hypothesis, but it is wrong, but it is false. So then again, you're making the wrong decision. So we'll kind of look at this in terms of like a jury convicting somebody or not convicting somebody. And that's about the easiest one to understand. Sorry, I do have to find my mouse. I don't even know where my mouse is right now. Okay, there we go. Look, I can use my scrolly roll thing. Okay, and then we're going to look at that kind of stuff on a graph now. So, H naught is true, H naught is false.
Hey, that looks like a Punnett square.
Yep, that's kind of what I was going to say, but I didn't know if you guys had done that.
Yeah.
Reject H naught or do not reject H naught. And then if it's true and you reject it, that's a type 1 error. If it's false and you don't reject it, that's a type 2 error. But in these two cases, you're actually making the right choices. And it's not like how it's different from a Punnett square is that it's not like 25, 25, 25. It's not those kind of options there. How many more slides do I have? Okay, I do have a lot more slides. Okay, you have that guy down. Okay, the level of significance is the maximum probability of committing a type 1 error. That probability is symbolized by alpha. So that's kind of the one that we're going to use a lot for alphas. We're going to have lots of alphas in there.
So type 1 error is just alpha?
Yep.
Okay.
The probability of the type 1 error, I guess. Probability of type 2 error is beta.
Oh, that's fancy.
Yep. Just kind of the same ideas of things that we've been doing is everything's going to have pretty much these same significance levels. We're going to use 10%, 5%, 1%. Make sure everything we do with the percentages, if I say a percent, write it as a decimal. Okay? Basically the same thing I just said. We're going to have critical values. Critical values are coming from the region, separates the critical from the non-critical regions, which just seems like, okay. So critical or rejection regions is the values that are basically on the ends of our, if you think about it in a graph. Let me see. Am I going to have a graph sometime soon? Okay, I'm going to draw a graph. I'm thinking I should have it pretty soon up here. Let me click a couple more times. Okay, yeah, we will have it soon. Okay, so I won't draw. You don't have to look at my drawings. Okay, non-critical or non-rejection is the range of values of the test that indicate there's no difference in what we said. This is just really, really wordy. Sorry about this. So you're non-critical, just make sure when we draw our graphs that you're going to label these two things. Okay, so critical is we're going to reject it. Non-critical is we're not going to reject it.
Critical, we're going to reject it.
Yep, null is rejected. So basically, null, rejected for critical or rejection. Non-critical and non-rejection, null should not be rejected. We can't say that it's true, but what we're going to say is that we don't reject it. Which kind of seems backwards because I think most of the statistical things that we hear about is that, oh yeah, we think that that's true, but really all we're saying is, well, we're not saying it's not true. You know, that's kind of like, you know, like Pinocchio on Shrek trying to lie about things.
Yeah.
well, I can't say that I don't know where they're not, but, and that's kind of how it is. That feels that way a lot, but yeah, totally feels that way. And then the other guy's finally just like, Betas, why are they here? And yeah, that's totally how we feel. Okay. So, our critical region, so this is like a picture for the right-tailed test. So we're going to have a slightly different picture for each of the different tailed tests. So our critical region for alpha of 0.1. So basically you would have the same picture for each value, and gosh, I hope it's not for each thing. For right-tailed test, so let me see what we can click on.
Is this picture in our book?
Not necessarily. Yes, it is in your book. It's on page 407.
Okay.
Yep. Okay, so mostly what we're doing, if we are finding the alpha of 1%, so we would have like a value of like, you want to be within 1% confidence type of thing. I don't know that they're going to use the word confidence intervals anymore. Critical values, they just say critical values a lot. Okay, so what we're doing, remember that corresponds to the bottom 99%. Bottom 99%, okay, and it tells you when we're using the bottom 99%, we're going to use 2.33 because that's the closest. Okay, so just remember that's when you're going to use a lot. Okay, what we really care about is that area up above that little piece. And we're going to have z-scores that correspond to it. Okay. This guy finding the critical values for a left-tailed test. So remember, the only thing that's going to tell you whether you're using right or left-tailed, most of the time it's not going to tell you, hey, use the right tail, use the left tail. It's just going to say less than or greater than somewhere in there. And it might not even use less than or greater than, it might use some other higher, lower, tons of different words that you can use for that. Okay, left-tailed test, bottom 1%. Bottom 1% looks like that. And we're doing the same thing, negative 2.33 for z-score. Okay, two-tailed test is, we kind of done a little bit of that. It's kind of like finding the z
Are we gonna have
alpha
to
over
find
2.
all this on homework today?
Yeah, you will. That's what you'll be doing today. Okay, and it's all just using that z chart. So in here it says z's, so make sure you're using the z chart. So non-critical region is the in-middle piece. Critical region where we're rejecting stuff is that outer piece. Okay, in case you wanted to write this down, for a two-tailed test of alpha of 0.01, your z-score would be negative 2.58 and positive 2.58. So you could write like z's, like, I don't know, I would kind of mark it for, I would keep it handy. Like I would write two-tailed for alpha is 0.01, my z-score is plus minus 2.58. And I would make like a nice little page or something just to keep all of this handy for yourselves. Okay, I have to scroll, plus minus 2.58. Okay, so after you write your thing, so your main thing is to draw the figure and indicate the appropriate area. Okay, I don't know if you guys just want to take a picture of this, because my God, it's long.
So do we have to just draw it every time?
I like to. I don't know that I can do it without drawing it for myself every time. And you don't have to make it big, you can fit it all in like a single line. Okay, if the test is left-tailed, the critical region with the area equal to A, I have to scroll here too. Okay, with an area equal to A, it will be on the left side of the mean. Okay, if the test is the right-tailed with an area equal to A, it will be on the right side of the mean. If it's two-tailed, the alpha must be divided by 2. 1/2 of the area will be to the right, 1/2 will be to the left. And what you're doing there is you don't have to go find the positive and the negative. It will be the same plus and minus. So you'll just do a plus minus with it. Kind of how we did for that guy. Okay, step 2. So we have it basically separated again. For left-tailed, we're using the z-value that corresponds to the area equivalent in table E. For right-tailed, we have to subtract 1 minus A first. For a two-tailed, we're splitting it in 2, and then we're subtracting that. And you'll just have the positive and negative. It doesn't really matter that you subtract it. If you don't subtract it, just make sure you're finding it and you're doing a plus minus with it. Do you want to take a picture of step 2 too?
Oh, yeah.
So that we're not, yeah, it's long, but there's lots of rules, but it's just, okay, which one am I doing? Okay, now I have to look at that one. Whoops, did you guys get that? Because it didn't even, okay. Okay, next example, we're actually going to do some of them. Use Table E and Appendix C to find the critical values for stuff, basically, just stuff. I don't want that one particularly. This is what I like. A left tail test with alpha equals 0.1. So you're finding these guys. Is that the same one? Okay, yeah, example 8-2. Okay, so I think your whatever table it tells you is your Z test or your Z score table. Mine is A that I have here, table E. Yep, so just use this handout stuff, or you can use the back of the book. I don't care which one you guys actually use. Okay, so I have a left-tailed test with alpha equals 0.1. So this is where I like, does it actually draw it for you? So it actually already draws it for you. Okay, so draw the figure. So you're going to draw a real fast normal curve, kind of draw 10%. This is definitely not where 10% lives. You're just going to do a really quick graph. Okay, you're looking on your graph over here, so I'm looking on my graph. So 0.1, left tail, remember, I actually get to use this guy, so 0.1 somewhere in here.
And that's just our normal chart?
Yeah.
Like, on there?
Mhm.
Like, okay.
I have 0.0099 is closer than 0.0102, so I'm going to use the negative 2.33. Oh, never mind. Maybe I'm not. What the heck does it have? Oh, because I was looking at 0.01. I don't want to use 0.01. Make sure you find 0.1. So now I have to actually find 0.1. 0.1. Make sure you're doing the right one. I guess it's really easy to not do the right one. They have negative 0.28. So yeah, so I can find over here, I don't know how well you can see this, so I have negative or 0.1. Yeah, so now we're actually back to using this a lot and it's useful again. I like this one because it kind of makes more sense. Okay, draw the areas. Now I want a two-tailed test with alpha as 0.02. Okay, so now if I divide that by 2, so anytime I have a two-tailed test, you're going to divide it in 2. So basically just to get over here and over here. Okay, you can just click and it'll draw it for us. Okay, so you do that quick drawing, label a little bit of stuff in there. I like just finding this one because I don't have to subtract it from 1. So the directions that you took a picture of said to subtract it from 1. I don't like that so much because if I could just over here where I